architecture. The first part, single processor system. Most computer systems use a single processor. On a single processor system, there is one main CPU capable of executing a general-purpose instruction set, including instructions from user processes. Almost all single processor systems have other special-purpose processors as well. They may come in the form of device-specific processors, such as disk, keyboard, and graphics controller. Or on mainframes, they may come in the form of more general-purpose processors, such as I/O processors that move data rapidly among the components of the system. All of these special-purpose processors run a limited instruction set and do not run user processes. Sometimes they are managed by the operating system, in that the operating system sends them information about their next task and monitors their status. So, second part, multiprocessor system. Within the past several years, multiprocessor systems, also known as parallel systems or multi-core systems, have begun to dominate the landscape of computing. Such systems have two or more processors in close communication, sharing the computer bus and sometimes the clock, memory, and the peripheral devices. Multiprocessor systems first prominently appeared in servers and have since migrated to desktop and laptop systems. Recently, multiple processors have appeared on mobile devices such as smartphones and tablet computers. Multiprocessor systems have three main advantages. The first, increase the throughput. By increasing the number of processors, we expect to get more work done in less time. The speed-up ratio within processors is not n, however, rather it is less than n. When multiple processors cooperate on a task, a certain amount of overhead is incurred in keeping all the parts working correctly. This overhead, plus contention for shared resources, lowers the expected gain from additional processors. Similarly, n programmers working closely together do not produce n times the amount of work a single programmer would produce. The second advantage is economy of scale. Multiple processor system can cost less than equivalent multiple single processor systems because they can share peripherals, mass storage, and power supplies. If several programs operate on the same set of data, it is cheaper to store those data on one disk and to have all the processors share them than to have many computers with local disks and many copies of the data. The third advantage is increased reliability. If functions can be distributed probably among several processors, then the failure of one processor will not halt the system, only slow it down. If we have 10 processors and one fuse, then each of the remaining 9 processors can pick up a share of the work of the failed processor. Thus, the entire system runs only 10% slower, rather than failing altogether. Increased reliability of computer system is crucial in many applications. The ability to continue providing service proportional to the level of surviving hardware is called graceful degradation. Sometimes so beyond graceful degradation and are called fault tolerant, because they can suffer a failure of any single component and still containing operation. Fault tolerance requires a mechanism to allow the failure to be detected, diagnosed, and if possible, corrected. The multiple processor systems in use today are of two types. Some systems use asymmetric multiprocessing, in which each processor is assigned a specific task. A boss processor controls the system. The other processors either look to the boss for instruction or have predefined tasks. This scheme defines a boss-worker relationship. The boss processor schedules and allocates work to the worker processors. And the most common systems use symmetric multiprocessing, in which each processing performs all tasks within the operating system. SMP means that all processors are pairs. No boss-worker relationship exists between processors, such as this figure, symmetric multiprocessing architecture. In this figure, that each processor has own set of registers, as well as a private or local cache. However, all processors share physical memory. The benefits of this model is that many processes can run simultaneously. N processes can run if there are N CPUs without causing performance to deteriorate significantly. However, we must carefully control I/O to ensure that the data reach the appropriate processor. Also, since the CPUs are separate, one may be sitting idle while another is overloaded, resulting in inefficiencies. A multiprocessor system of this form will allow processes and resources, such as memory, to be shared dynamically among the various processors and can lower the variance among the processors. Virtually all modern operating systems, including Windows, Mac OS X, and Linux, now provide support for SMP. The difference between symmetric and asymmetric multiprocessing may result from either hardware or software. Special hardware can differentiate the multiple processor, or the software can be written to allow only one boss and multiple workers. A recent trend in CPU design is to include multiple computing cores on a single chip. Such multiprocessor systems are termed multi-core. They can be more efficient than multiple chips with single cores because on-chip communication is faster than between-chip communication. In addition, one chip with multiple cores uses significantly less power than multiple single-core chips. It is important to know that while multi-core systems are multiprocessor systems, not all multiprocessor systems are multi-core. In our coverage of multiprocessor systems throughout this text, we generally use the more contemporary term multi-core, which excludes some multiprocessor systems. Clustered systems. Another type of multiprocessor system is a clustered system, which gathers together multiple CPUs. Clustered systems differ from the multiprocessor systems described above in that they are composed of two or more individual systems or nodes joined together. Such systems are considered loosely coupled. Each node may be a single processor system or a multi-core system. We should know that the definition of clusters is not concrete. Many commercial packages wrestle to define a cluster system and why one form is better than another. Clustering is usually used to provide high availability service. That is, service will continue even if one or more systems in the cluster fail. Generally, we obtain high availability by adding a level of redundancy in the system. A layer of cluster software runs on the cluster nodes. Each node can monitor one or more of the others. If the monitored machine fails, the monitoring machine can take ownership of its storage and restart the applications that were running on the failed machine. Clustering can be structured asymmetrically or symmetrically. In asymmetric clustering, one machine is in hot standby mode while the other is running the application. The hot standby host machine does nothing but monitor the active server. If that server fails, the hot standby host becomes the active server. In symmetric clustering, two or more hosts are running applications and are monitoring each other. This structure is obviously more efficient, as it uses all of the available hardware. However, it does require that more than one application be available to run. Other forms of clusters include parallel clusters and clustering over a wide area network. Parallel clusters allow multiple hosts to access the same data on shared storage. Because most operating systems lack support for simultaneous data access by multiple hosts, parallel clusters usually require the use of special versions of software and special releases of applications. Some cluster products support dozens of cluster technology is changing rapidly. Some cluster products